Okay, so first let's go through logistical stuff. Our final, exam 5, is Thursday, so a week from today. That's the 10th. From 11 a.m. to 1 p.m. in whatever room this is. I think it's C2040 here. It's cumulative, so what I would recommend doing, I think it's probably the case that most people don't have the time or inclination to go back and do every problem again. That's a lot. But what I would recommend doing is start with the vectors problems, start at the beginning, and just look through the problems and ask yourself what the steps are, And if you immediately know, like I do this, 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 then don't waste any more time on that one. And when you get to the ones where you don't remember the idea of it, then refresh your memory on those. Spend a little time working through those. If you get to the point where you could, where any question, any homework question, you could explain to someone else why you could do it and explain at each step, like why you did the step that you did, then you'll get, basically a perfect score on the final. Any questions about the final right now? I'm planning to go through a little outline of all the topics, just sort of as a reminder, but okay, and then grading. Exam 4 will be graded first thing tomorrow morning. And so that's a puppy promise. And so you can email me to set up a time to meet, or try just stopping by my office if you want to pick it up. I will, on D2L, I'll put up my office hours for finals week. I know Monday and Tuesday are going to be the usual ones, but then I start having finals and stuff that I have to give. So, but I'll think about that and put them up. But Monday and Tuesday will be the same as always. So finals week, office hours will be Monday 11 to 11:50 a.m. in the tutoring center. Tuesday 11 to 11:50 in the tutoring center, and then the rest will be posted on D2L. So those are times you can pick up your binders if you don't have them, your exams if you don't have them, whatever you want, or we can talk about stuff. Yes? No. If anything, it'll be easier so I can fit a few more, like simpler problems, so I can fit a couple more in. It'll definitely be sort of on the easy side. So yeah. definitely nothing harder. And I mean, there are always people who get perfect scores on the finals, and that won't change this semester. Yeah, you won't. I mean, it's going to be the same length of test as the other ones. There probably will be a couple people who stay the full 2 hours. There usually are, but most people will be gone way before that. You know, 4 seems like usually the average number of questions on any test, and maybe if I make them a little simpler and shorter, then there might be 5 or something. You know, or if I put on more than one vector question, those are so fast, maybe it would be 6. But so let's say 4 to 6, depending on the type of problem. But I'll write it to be about a 60 to 75-minute test. That's the idea. No, it's going to be. That's a good question. In statics, they tend to be sort of combined, but generally, I mean, they're going to be the same as the practice problems, those same kind of questions. So I'm not going to do any combination of things that you haven't seen already. Any other questions? Okay, I want to do one more friction problem, and then I'll go into sort of an outline of the class. So this is a combined bearing problem. So this is a journal bearing and a thrust bearing. And this is the kind of thing that you could have to deal with if you have a pin joint that supplies thrust. So remember, a pin joint, you can't have a pin joint where the pin can just slide axially, freely, and then that doesn't produce any axial force. So that means no thrust. But there are also types that have little flanges on the, it can be there's a lot of ways you could do it, but a common one is that you have flanges on the 2 sides that keep the pin from sliding. And those are the pin joints that provide thrust. And in a case like that, if you have friction, you could have journal bearing friction as the pin tries to rotate. And you could also have thrust bearing friction as the pin moves against the flange, for example. So here is what I'm picturing. So let's say that you have something like this. And this pin goes into this hole. This could be like a wall or something. And let's say that here on the pin, we have a radius of 0.01 meters. And here on this flange, we have a radius of 0.05 meters. And let's say that the coefficient of static friction is 0.5. And let's say that So there have to be forces applied to this in two different directions to apply these two kinds of friction. The thrust friction will be caused by pushing the flange of that pin against this wall. And so that, let's say that's a 5,000 Newton force. And then the journal bearing friction is going to be introduced by, once that pin goes through that hole, you have downward forces pushing on it. So let's say this is 2,000 newtons here and 2,000 newtons here. And we want to know what external moment must be applied to initiate rotation. Can everyone picture what the idea of this problem is? Okay, so when this is in position to rotate it, these forces are going to make there be friction between the inner surface of that hole and the pin. And then the thrust friction is going to act between the flange, the side that's sort of obscured in this picture, and this part of the wall. So, and we can just do it separately. We'll get a moment that's produced by that journal friction, and we'll get a moment produced by that thrust friction, and then we'll just add them up. Yep. What? Is it a solid? Oh, I see. For the thrust, well, there won't be any thrust friction on the pin part. So yeah, it is going to be a hollow circle. It's just going to be it's just going to be the contact area for the thrust friction is going to be from the outside of the pin to here. So that radius, when we do that integration, is going to be from 0.01 to 0.05. All right, so let's first do the journal bearing friction. So I'm going to draw the axle from the side. Remember when I made that hilarious Axl Rose joke? That was so good. I was on fire that day. I'm going to tell people about that forever. Okay, so we have a downward force of, what's this downward force here? 4,000. It's the sum of those two forces, the total force on the axle. And that means that we have an equal and opposite force of 4,000 over here. And that force is made up of two perpendicular forces, a normal force like that, and a friction force like that. So here's normal force N. This is the friction force 0.5 N. And this angle theta is equal to this angle theta. So this is 0.5 N, this is N. And so theta is equal to the inverse tangent of 0.5 N over N. And the N's cancel out, so it's just the inverse tangent of 0.5. What's the inverse tangent of 0.5? That's what I was going to say. 26.5651 degrees. The only reason that we're calculating this is to find this moment arm. This is what we want. And that moment arm, so we're going to use that angle we just got, and we know that this radius is r. And so that moment arm rho is equal to r times the sine of 26.5651 degrees. So that's 0.01 times sine of that angle. And what do you get for that? .4. Yeah. Okay. So 0.00407, right? 47 meters. And so now the moment is just equal to that moment arm times the force of 4,000. And what do you get for that? .88 Newton meters. Okay, so we'll come back and use this later, but that's the moment that's required just to overcome the journal bearing friction. And now we have to account for the thrust bearing friction. Okay, so we're dealing with a hollow, a hollow ring like this, where this radius is 0.01 and this radius is 0.05. And we're going to do this by breaking it up into infinitesimal rings, like that. And this infinitesimal ring has a thickness, dr, and a total infinitesimal area of 2 pi r dr. And now we can go on to those 5 steps. So the first step is to figure out what the force is per area of contact. So the force per area is the total force divided by the total area of contact. What's the total force that matters for thrust-bearing friction? That guy didn't do it, but it just reminded me of one time that a kid in the last week of classes, like there was a new student in class, and I was like, oh, like someone's friend is here with them or whatever. And then he came to the next class, and I was like, wait, he's still here? Like, that's a long visit. And then he came to my office and was like, I've had a lot of like personal things going on this semester. Is there anything I can do to catch up? Like in the last week of class, I'd never seen this guy. Don't do that. Yeah. So I was like, yeah, if you go to the Bell Museum and write a summary, you can have a B in the class. Not really. Yeah. Um, okay, so yeah, the force that matters here is the 5,000. And what's the area that matters for doing this? We're talking about the total area of contact. So that's going to be pi r, well, pi times r outer squared minus r inner squared. R outer is 0.05. Our inner is 0.01. So let's keep the pi and calculate everything else. Can you tell me what? So we're going to have some number over pi. Can you tell me what that number is? .002. I can't do it. It's going to be really big, though. And now the second step is to figure out, for a given one of these infinitesimal rings, what's the total normal force on that infinitesimal ring? Well, since it's an infinitesimal area, it's going to be an infinitesimal normal force. So I'm going to call this d normal. And that's equal to 20.83 times 10 to the 5th over pi times the area of the infinitesimal ring, which is 2 I r dr. I have to keep that as r because we want a general expression for any infinitesimal ring depending on what its radius is. And so the pi's cancel here. And we get 41.66 times 10 to the 5 r dr. Now that we have that normal force, we can figure out the friction force. So the infinitesimal friction force produced by that ring is the coefficient of friction times that infinitesimal normal force, 41.66 times 10 to the 5 r dr. And that's 20.83 times 10 to the 5th r dr. The thing that makes this infinitesimal is having that dr there. And now that we have that friction force, we know that that friction force acts at a moment arm of r. So now we can figure out the infinitesimal moment produced by that friction force. So this is r times the infinitesimal friction force, and so that's 20.83 times 10 to the 5th r squared dr. And now the last step is just to integrate that from 0.01 to 0.05. So the total moment is the integral. Let me pull the constants out. So it's 20.83 times 10 to the 5th times the integral from 0.01 to 0.05 of r squared dr. And so that's 20.831. I can't do it. So what do you get if you divide this by 3? Okay, so we got 6.94 times 10 to the 5th times r cubed, evaluated from 0.01 to 0.05. And what do you get for that? That sort of S-shaped thing is an integral sign. (127.7 Newton meters). And so in order to initiate motion, then the total moment required is 17.88 plus 127.7. And what do you get for the total? 145.58 Newton meters. Okay, any questions about either of those? Okay, well, let's just go through an outline of the topics that we've covered. So I'll break it into 7 main sections, and then we'll give a little detail when it seems to make sense to me about what each of these topics dealt with. So the first one was that vector review. So you have to know how to use dot products and cross products. And then we got into statics. So the first one was particle statics. And maybe the main distinction between particle statics and rigid body statics is if you're dealing with particles, there's no orientation. So there's Newton's second law, but there's no rotational Newton's second law. Okay, so if you're in 2D doing particle statics, you only have 2 equations of motion, 2 Newton's laws. If you're in 3D, you have 3 of them. We did the first stuff related to joints and forces with known directions. So we dealt with cables and pulleys. We dealt with frictionless contact. And friction contact. But none of the stuff yet with fixed joints and pin joints and all that stuff. And then after that, we got into rigid body statics. When we switched from particles to rigid body statics, we had Newton's second law and the rotational Newton's second law. So that means 3 total equations in 2D problems and 6 total equations in 3D problems. And the main thing that was new in rigid body statics was dealing with joints. One thing I should say about this, so anytime you're dealing with rigid body statics, you can always use that, row moment table. A lot of times we didn't, because with problems where the things are horizontal or vertical, it can be a little quicker to just think of the moment arm and the direction of rotation and stuff. But anytime you're dealing with rigid bodies, you could do it this way if it helps or you get confused or whatever. Okay, but the main thing that we were dealing with was joints. And the joints were broken up into joints that introduced one variable into Newton's laws. So what are the types of joints that introduce one variable? So those are all the forces with known directions. Like a normal force in it's frictionless contact. And then there was a pin and slot joint. And you could also say rollers. And then there were the joints that introduced 2 variables. This is the 2D joints. So the ones that introduce 2 variables are pin joints. And friction contact. So the difference between these two is these are force with a known direction. This is a force with an unknown direction. And then in 2D, well, yes? No, that's like if you're talking about, so if you have, something like that and it says that makes contact with friction there, then in your free body diagram, you just write that as. And so we don't calculate anything about what the friction is. We just know that it applies forces in both directions. Well, if it says friction, then you don't make any distinction about direction. You have both of those as unknown variables. If there's no friction, then then it's perpendicular to the surface. And then in 2D, there's only one other possible type of joint. There's only 3 degrees of freedom because there's only 3 equations of motion. And so this one is a fixed joint. So this is a force with an unknown direction and a couple. And then we add the 3D joints. And this one, well, there can be up to 6 variables introduced in these. Let's think about what some of those are. Let's see. So the first type is frictionless contact. And ball rollers. That's like a roller that doesn't have a preferred direction. If you're thinking of like a wheel has a preferred direction, and so that doesn't fit here. And so the only force that's applied there is perpendicular to the surface in those two cases. Then you could have like a wheel that allows motion in one direction, but keeps from sliding in one direction and keeps it from translating into the surface. Then 3 variables are introduced by something that totally restricts translation. So what kind of joint restricts all translation but allows all rotation? Ball and socket joint, yep. Then we get into the sort of tricky ones. Okay, so remember this. What kind of joints do we have that occasionally, that change the number of variables they introduce depending on the setting? These are pin joints. Remember pin joints in 3D. And so the up to is these pin joints can apply couples if there's nothing else to prevent the thing from changing orientation. But if there is something else, then they're not going to apply those couples. So 4 variables is a pin joint without thrust. And up to 5 variables is a pin joint with thrust. So when is it that you don't, and okay, so the 4 variables would be in a pin joint without thrust, 2 translational directions, but not, if there's no thrust, then there's no force along the line of the pin. And then also 2 couples, but those couples don't always occur. So when is it that those couples don't occur? That's right. So if that pin joint is working with another pin joint that shares the same axis, then those couples don't show up. if there's not another pin joint sharing the same axis and it's working by itself, then it will provide couples that prevent a rotation this way and a rotation this way. You kind of normally don't want to require a pin joint to supply those couples, though, because it's a good way to break the mechanism. And then it's exactly the same thinking for a pin joint with thrust, except there you also have a force that prevents translation along the pin's axis. Okay, and then in 3D, what provides 6 variables? Fixed joint, yep. And that's because there are only 6 degrees of freedom for a rigid body in 3D. Any questions about any of those? Okay, then we got centroids. And we use centroids for 2 things. One, we used it to find where we could apply the weight force. And then second, we used it to represent distributed loads as point forces. And really, those are the same thing because weight is a distributed load. But at that time in the class, we hadn't started thinking about weight as a distributed load at all yet. And then we got into what I consider to be the most important topic in this class, structures. And I think the main tricky thing about structures calculations is choosing a place to, so choosing a body to associate the joint with. Once you do that, all the bookkeeping gets a lot easier. The one I always choose is the lowest numbered member, but there's no mathematical reason you have to do that, and it works out the same even if you number the bodies differently, so it must not be that important. But what is important is that you have a system that tells you what body to associate the joint itself with, so that you don't double count forces that are acting at the joint, and you don't double count reaction loads between bodies. So. And then we talked about internal loads and beams. And so that one's where we calculate the internal tension. The internal shear force, and the bending moment. And we calculate all of those as functions of x. And then the last topic was friction. And I broke that up into 3 separate sections. So the first one was square threaded screws. And for the numbers that I give you, you need to be able to derive this one, just like the way I did it in example problems, you know. And then the second category was belt friction. That's just a formula. You don't have to derive anything for that. I didn't derive it. It's a little complicated deriving that one. So that's definitely the easiest of the 3. And then we did bearings. Yeah. Yep. So I'll give you the formula if there's a problem like that, and it's not a very interesting, you know, that's not a very interesting kind of problem, but I would give you the formula and you just have to use it. And bearings is broken up into journal bearings and thrust bearings. And all of these, you need to be able to go through the steps of deriving it, you know, for the specific numbers I give you. And that's it. Anybody have any questions about any of that? Yep. No, I mean, so it's sort of somewhere in between. I want you to, so like, it's like what I did here, you know? So I didn't derive a general formula, but I went through the whole process that you would use. I just had numbers in place of constants and stuff. Any other questions? Yeah. Just like what we just did. So for a journal bearing, it means draw the free body diagram of that axle, draw those angles, calculate the angle, use that to calculate rho, you know. I mean, I'm pretty flexible on what you put on there and stuff, but I want you to be able to, you know, think through the process of coming up with that besides just using a formula that I derived. Any other questions? Okay. Well, thanks for taking my class. Probably see a lot of you in the future. So test is Thursday at 11. So don't miss that. Okay. And